Hello everyone. So I want to go over our first homework. Um, I have explained elsewhere what the dynamics, the protocol is when homeworks. So in particular, I have always these two special problems that I assign per topic, and only those I solve. And that's this video. This is the solutions of these two special problems. So check your answer against this one. Don't forget that most problems, homework problems, have a solution at the back of the book. So also go check your answers with the back of the book. But of course, that is much less helpful because that doesn't tell you how they got there, just what it is. And sometimes even small mistakes might lead to different answers that you think, oh, I completely messed this up, but perhaps you didn't. So that's why I want to give at least two completely worked out examples. And okay, let's dive in. So this is, of course, on linear first order equations, and we know that there's two steps we have to do. Step one is, well, two steps, there are many steps to do. The first step we should do is look at the complementary homogeneous equation. That means, now remember that the typical form would be this way of a linear first order differential equation. It's not exactly in that form. There's this 1 plus x in front of y prime, so we could divide this out already, and let's do this. There's no reason not to do this, so I'm going to do this. Is sine x, and of course then since I divide by 1 plus x, I get this squared here in the denominator. Okay, so it is, you don't have to do this, but at some point you will have to do this, so why not do it now? Okay, so the homogeneous, this keeps doing this. The homogeneous equation that we want to therefore have to deal with first is this one. Remember, it's the part where you put the f equal to 0. So there's only a y prime and a term with y. There should be only two terms. Okay, because we're going to solve so that the y is on one side and the x is on the side. This is separation of variables, which you also see in the next lecture. We have talked about this now. You've heard of this method, and that's really what the method is. Okay, so in other words, the first thing to do is bring this to the other side. That becomes a minus sign. Be very careful with all these little minus signs and little some mistakes are easily made, and unfortunately, a mistake in the beginning can lead to a big difference in the end, and sometimes even to unsolvable problems. So we have to bring the y prime to here, and then we are good. Okay, so we can integrate here. Remember, this was always if you can write it this way, and when we talked about separation of variables, we said, well, perhaps it is easier to write it this way, and then just take integrals. Sorry. Let me back up a little bit, because otherwise I lost you. So replace y prime by dy dx and bring the dx to the other side. I forgot to write the dx here. And then you integrate. Okay, the antiderivative of this is ln of y, absolute value of y of naught. These kind of things I'm going to kind of go over with. We're going to have to be a little bit more careful when it comes to initial values, initial conditions, because then, of course, it matters sometimes. But for now, I'm just going to ignore it. And then deriving this here. Sorry, where does the x come from? Okay, I'm backing up one more time, because otherwise I'm going to lose you. Sorry. I wrote x and I meant to write dx. I'm sorry. So from here to there, the only thing that I'm writing is y prime is dy dx, and I bring the dx to the other side. I'm so sorry that I keep. I'm going too fast. Okay, for myself. So let's now take the integrals here. So this would be ln of y. What is that? Well, it's a 1 plus x in the denominator, so we know that this is also an ln. Oh, sorry, an ln. ln 1 plus x. Now we want to get rid of the ln's, but we have this negative 2 in front, but we know that we can bring this inside an ln and it becomes an exponent. Of course, a negative exponent will mean that we divide by it, but let's not do that for the moment. And the next thing we have to do is get rid of the ln's by taking the exponential of both sides, and that gives me y here, the exponential of ln cancel, and the same happens at that point. So that is what I get, and perhaps now it's more telling to write it without negative exponent. You might ask, is it important? Do we have to do this? No. I do really not care how your answer looks like at the end. I don't want you to simplify. In fact, I prefer you not to simplify. However, very often you will need to simplify because we need to do more with this thing. It's not just finished. Okay. Now we know that this one is also not finished because this is actually really the homogeneous solution that I found. So I'm going in the calculations I write y by when I get the answer, I put an h here, saying that this is the solution to this equation. But that's not what we want. We want the solution to the original equation, which has this non-homogeneous term. And what we then do is say we propose a particular solution. And how do we do that? We take a new function, u, or variable if you want to call it, and we say u times yh. And this is a very common technique in differential. It's strange that this works, but it somehow miraculously always works. Not always, sorry, but often works, and especially in the case that we will see, is that you just say, okay, take a solution of from your homogeneous, or take a solution that you somehow find, and now look for a new one where u is a function that depends on x. U depends on x. Let me write it that way. Okay. So what does this mean in this? So this is the formula, but again, I don't want to keep dragging these p's and h's around. So when I start working with it, I'm going to just write y, and then u. Now, of course, I have to replace this by the function that I just found here, 1 plus x squared. So this is what I'm looking for. Okay, what do we do with this? So this is if you want, step 2, right? This is the proposed. So we propose a solution of this form. And that means we have to determine what u is. How do you do that? Well, now you plug this in. So you're going to plug this into the original equation. Of course, it requires us to take the derivative. And as a product, well, you could say it's a quotient. Okay, some people might say it's a quotient rule. I kind of don't like the quotient rule. I get confused where the minus goes, so I keep thinking of this as, now there's a product. And so the derivative of the first, copy the second, and then copy the first, take the derivative of the second. Now, of course, in that case, I have to think of it not as in this form, but in this form, because I want to do the power rule, okay? So that would be then minus 2, 1 over x, 1 plus x minus 3, right? It's derivative, so the degree goes down by 1, and the coefficient comes out. Okay, that has to be plugged in. So this we're going to plug into the original equation, which I have to scroll up a little bit. And sorry, yeah, okay, this one, but we said we're going to use this one. Let's do this one then. Okay, so if I plug this in, I'm sorry, I cannot get everything on the same screen, but you can follow, right, that I'm doing it correctly. So we have u prime 1 plus 1 x squared. That's y prime, right? And no, that's not y prime. This is only part of y prime. Plus u times minus 2, 1 plus x. Sorry. Now I wrote the negative 3 in the denominator. That was wrong, right? I have to write it here. If I wanna keep the negative exponent, it's really not in the denominator, but it's in the numerator. Okay, let's make this over again. So this would be minus 2, 1 plus x to the power negative 3. See, these little mistakes are so easily made. So, and I'm recording this thing, and I could say, oh, stop, I'm going to do it over, and I'm not going to show my mistakes. No, I want you to see that I make mistakes, because that also will tell you, how do I recover from these mistakes? How do I recognize these mistakes, right? That is sometimes an art on its own, because you have to sometimes realize, oh, no, this cannot be true. So then you have to go back, and how do you find them? Okay, so this is y prime, and then we have to add the next term, 2 plus 2, 1 plus x times y. That was u over 1 plus 1 x squared. Okay, and that is equal to the non-homogeneous part, f sine x over 1 plus x squared. Sorry, we have to look here, right? Sine x over 1 plus x squared. Okay. Now, what has to happen is there has to be some calculation. In fact, in this case, we know that the u term has to disappear. And that's exactly what happens, right? Because what we have here is minus 2, 1 plus x cubed times u. And what is this one? It's the same thing. It's 2u over 1 plus x cubed, but with a positive sign, so they cancel out. These two cancel out. So then I'm left with this one. And that's, again, a separation of variables, but really a simple one. Here we're going to just solve for u prime. That means I'm going to have to multiply both sides with 1 plus x. Sorry, I copied it wrong, right? See, I was already realizing I'm going to get an integral that I don't know how to solve. Because what I have made mistake is there's a square here. So there's a square there. Right? So if I would not have the square, let's see what would have happened without the square. So I'm going to get myself... see how I get in trouble. This 1 plus x would go here, right? So I would end up with sine x, and only one of the 1 plus x's would cancel. Sine x over 1 plus x, I have no clue how to integrate that. It sounds simple, but I have no idea. You think integration by parts? No, it doesn't work. These are just these simple integrals, but perhaps there's a method to solve them, but I don't know them. So luckily, this is not the case. What we have is there's a square here, and now, of course, if I cancel out, it becomes very nice. The 1 plus x squares cancel both sides. So you see that these problems have to be when you make a problem like this, when I make a problem for this for you on the quizzes, it is very delicate. The functions, I have to make it really right, otherwise it gets impossible for you to solve. Now, this is not impossible, right? This is just antiderivative of sine is cosine. Is it minus cosine? Okay, u is equal, let's think about this. Yes, it's minus cosine, right? Cosine x plus c. Do I need a plus c here? No, not yet. So this is a little bit tricky. Depending on what method you use, you put a plus c later or beginning. Okay, so here we did in the homogeneous, I didn't write a plus c, not at least at the part where I needed it. I needed this for here, right? I'm just going to plug it in here. But now I have to put everything together, and now I have to think. So the general solution will be, you take this one particular solution we found, and this is really one, plus the general homogeneous. So this is the general, general homogeneous solution. Now I didn't write up the general one. What I miss? What was missing in my general one? A plus c. That's the only thing. Well, here the plus c. Oh no. Be careful. Now, see, I'm already making a mistake. Let's call it plus d here. Now I'm taking exponentials. Now what happens then? You have to be careful, right? So let me erase this here. So I have to take the exponential of this. So it is e to the power ln 1 plus x minus 2 plus d. So the cancellation doesn't happen right away with the e and the ln because it sits inside of a sum. But luckily, that one splits up as a e times d times e to the ln 1 plus x to the power negative 2. And now the e and the ln cancel. And e to the d is a constant that I'm now going to call c. That's why I use a d here and so, because I like to be my constant in the end to be called c. But that's not important. If you have a preference for another letter, like your initial for your name or something, use that as a constant. As long, of course, I hope your name is not Xavier, because then you don't want to use an X or something like that. Okay, so here we go. So this is this C. I'm rewriting my constant, and then these two cancel out. I would have 1 plus x to the power negative 2, if you want, C over 1 plus x squared. Okay, so now I'm saying this is what I have to put together. So I get minus cosine x. Okay, what is yp? Right, but yp is, remember, it's u times yh, the special one that I chose here. So it is this one. Okay, so there is a 1 plus x squared also that comes here. Don't forget that part. So this is not u, right? This is not u. U is just part, is a help, is an auxiliary variable, because we know that the solution, or the particular solution, let me now make it more clear, is this. So we have to do minus cosine x over 1 plus x squared. I mean, multiplying, of course, I can write it this way. So this, and I forgot my parentheses. Very important, of course, because it's different. If I don't write parentheses, I get something else. And I would be in trouble. Well, not really, but okay. So what is my general solution now? So the general solution y is this specific solution that I just found, this one, plus the general solution which I wrote down. Where I wrote it down here. Now I fixed it, right? This is this guy. Is it that way? Yeah, it's that one, right? Plus c1 plus x squared. And actually they are on common denominator, so it's kind of almost a sin not to put them on common denominator. But again, if you didn't, I'm not going to subtract points for that. So that's the solution to your first homework problem. This didn't have an initial value, initial condition. The next one has, so let's go to that one. So here we do x squared minus 5y prime minus 2xy equals minus 2x x squared minus 5, and we want y2 to be equal to 7. And again, you might say, oh, awful, 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 but sometimes the awful, it might not be bad, okay? So, same strategy, let's look for the homogeneous one. Well, perhaps we should, before I do this, let's again write it really as a linear. So this would be y prime minus 2x over x squared minus 5y equals minus 2x. The x squares minus 5 cancel out. Okay, that's the standard form of the way that we write it always. And it's a good practice to always get to the standard form, because then it's also much easier to recognize what the complementary equation is. The complementary equation, of course, is then the left-hand side, the ones that contain y. So the complementary equation, homogeneous one, is y prime minus 2x over x squared minus 5y equals 0. Now, y's have to go one side, the other one, so y prime equals 2x x squared minus 5y, and so this is y prime over y equals 2x x squared minus 5. And if you want, using the material from for today's lecture, is you can write it also as 2x dx x squared minus 5 here, because then it's much easier to see that that's what you're doing, is integration with respect to two different variables. So this is again ln y. That's always ln y, by the way, in the linear differential equation. If you separate variables, it's not, but for this case, it's always the same, because it always comes out this one. But here, of course, this can be anything. And how are we going to solve this? Okay, so this is the integration part, right? The calculus is going to be, we need to do all the techniques from calculus, and I try to always give examples of different types of calculus integration techniques that you maintain all of those. Remember, there's a view sheet if you don't remember anymore how these techniques work. What is this one? Well, it is you can say it is a rational function, so integration by parts. That is not something I would look forward to. Well, it's never something you look forward to, because it's always a bit work. But you remember, it means factoring the denominator, and whereas this is x squared minus 5, it would involve a plus or minus radical 5. And I know most of you go screaming and running away and calling for your mommy because you don't like radicals. We're gonna have to deal with them. So, okay, but that's not the best solution. There's a much easier one, and that's the one you always should look for. Is perhaps can just substitution work? And remember, substitution means that you have a function, the so-called inside function. There's not much inside here, except we consider denominators, sometimes even numerators, but denominators as being inside, right? There's something done to them afterwards. You divide by them or something. So. But you need an inside function, and the derivative of the inside function should be the only thing left, and that's exactly what is happening. So we do w equals x squared minus 5, and so then dw would be 2x dx. See how kind they have been to put this extra 2 here, because we get exactly the denominator, so it's dw over w, and that is just ln of w. Plus c. Let's do it now correctly from the beginning. So do the general equation. I'm going to use a d again because I know can change again. Take the exponential of both sides. So exponentiate. and that gives me y on this side. And here, of course, again, we have to do one extra step here. We have to factor out the ED, and then we have W. Okay, E and L and W cancel, and that, of course, becomes a constant C. So our solution is y equals CW. Is that the end? No, because, plus C? No, not plus C. Oh, my C is there. I'm sorry. I'm used to always teach calculus. This is the first time, actually, for a long time that I taught this, so I sometimes get this inclination, this natural reflex of putting a plus C here, but we have to be careful, right? The plus C, we did it already here. Okay, so that is CW, but that, of course, W, we have to write it in terms of the original variable. So y equals C times x minus square is the homogeneous solution. So I'm now going to write it this way for reference later, that I can go back to this when I need this, because in step 2, for one thing here I need it ready, is that I'm going to now use this formula. The particular solution is obtained by using the general solution, but here I can then choose. So here I can choose C equals 1. Remember, when you do this technique, you only need to work with one particular one, and you take the easiest one you can get. But except, of course, 0. You cannot 0 because it has to be a non-zero solution. Why? Because otherwise you're always going to get 0. If you do u times 0, it's going to be 0, right? So you're not going to find anything new. Okay, so that one's not going to work. So I take C equals 1. That means that, and you understand what I'm doing, right? This is the formula, so perhaps I should put it in a bit in a box. But when I do the calculations, I don't want these P's and H's and so, and I write down just y for yp, u is my new variable, and I plug in what I have here, x squared minus 5. Remember, I put C equals to 1. And this is what I'm going to deal with. So now I have to plug this in. So plug in the original equation. So we have to, first of all, find the derivative. That is u prime, derivative of the first, copy the second, plus u, take derivative of the second, and copy the first. Okay, and that we plug in into our original equation, which is here. Let me actually, there's a nice feature that I should use, because it, no, where is it? Where's my feature? Where's my scissors? Oh, is it then? Okay, this is my scissors. My scissors have changed. That's what you get with updates of apps. They think, oh, we're going to change something, and then you don't know anymore what's going on. Okay, here's my equation. Okay, so we plug this in. So plug this in here. We get u prime x squared minus 5 plus u times, yes, no. I said O, I don't know why I said O, this is correct, u plus 2x, minus 2x over x squared minus 5. This y, what is this y? This is the y, right? U times x squared minus 5 equals minus 2x. Okay. We need some calculation. In fact, to use it, terms have to cancel, and that's exactly what happens again. Look, I'll do it in a different color here. These two cancel out. And now we have minus 2xu plus 2u2x minus 2ux. So they cancel out. So let's do this. I'll do it this way. So they cancel out here. And that's exactly what needs to happen. If that doesn't happen, you made a mistake. Okay, so what we have now is u prime x squared minus 5 equals minus 2x. Okay, we have to bring this to the other side. Minus 2x over x squared minus 5. And then we have to do the integration. That means that u is equal to the derivative, the antiderivative of this guy, but we actually know this. We actually calculated it right here. It's the same calculation, except there was a negative sign. Now is the negative sign, and then not. So we know that the solution is x squared minus 5. And so with the minus sign, minus x squared minus 5. Plus C, but in this kind of thing, because I need a particular, the word particular is supposed to express this. You just want one. So I don't need to write the plus C or plus D or whatever. If you don't understand where this minus x squared minus 5 comes from, just look at the calculation here and work it out again, and you see you get exactly what I said it would be. Okay, so what is now, what is y therefore? Because remember, y is actually, the common mistake is to think, oh, this is u is a solution. No. This is where we have to go now, right? So y is equal to u, which we just calculated, times, x squared minus 5. Okay, that's what it is. So in other words, if you want minus x squared minus 5 squared, that is the particular solution. I'm going to write my p again because now I'm thinking of my formula again. Okay, so this has to go into my formula. No, sorry. The formula, I haven't written down the formula yet. So, because there's a new formula now that says the general solution, y, is a particular solution plus the general homogeneous solution. I'm sorry, this is a couple of steps where it's a bit, and the textbook, I wish it would be a little bit more systematic in that. He switches from y's to y1s and so on, and then says, okay, this is the y satisfying this equation 1.3.4.5.7.413, which is impossible to figure out what they mean. So make sure that each step we using y in a different setup again. So this is now the formula. So this is a new formula which says that I have to plug in this one in here as well as my homogeneous one that I should have also perhaps put in green, this one here. Okay. So we might say, why not this one? Well, this was part of the exploration in order to find what u was. Okay. Here I found what u was, and of course I want it without the u because I need to know what it is. U, it should be only in terms of x. So y, the particular solution is minus x squared minus 5 squared, plus the general homogeneous was c times x squared minus 5. So, no, okay. Now I see, you shouldn't do this, right? I said something which was wrong, right? Because the solution was not. See, this is when you take shortcuts, things go wrong. What did I say? What did I do wrong? I said the solution to this integral is x squared minus 5. No, that's not true at all. How can that be? This is a rational function. How can the derivative be how can the antiderivative be a polynomial? No, it is this guy here, but we never wrote out what ln was. So the actual solution, I should perhaps have done this here already here. It's better to do it as soon as possible. I kind of was a bit lazy here. I should have done it there. This is the solution. So, okay, so I got it wrong here. All right. So this is the part I got wrong. Okay, what did I get wrong? My u is not this. Sorry, my u is minus that minus sign. That part I got right, but that was the only part I get right. Minus ln x squared minus 5 plus a constant, but we said we don't need that. Okay, so remember this was the calculation here. Okay, so now the u becomes u times u. Sorry, it was u times. U times here, here. This u times x squared minus 5. So I erased a little bit too much here. So this becomes minus ln x squared minus 5 times x squared minus 5. That's the particular solution. And so this part is wrong here. So this is minus ln x squared minus 5 times x squared minus 5 plus c times x squared minus 5. Now, there is an initial condition. So this is where we have a step 5. And only at this point, when I have the general solution, I can start thinking about finding the initial condition. If I do it earlier, if I start looking it up, doing it with this constant c here, then I don't get the initial condition for the original equation because this is from the homogeneous, from the complementary, not from the original one. So now I'm going to put in, and the initial condition was, where was it? Oh, I didn't, did I write it up? The question, yeah, y2 is 7. So y of 2 is 7, so let's plug it in. 2 equals minus ln 4 minus 5 times 4 minus 5 plus c times 4 minus 5. Now, you see here already why there's a problem. Because ln 4 minus 5 is negative 1. That's not a problem except for here. And that is because I was lazy and I didn't put my my absolute values. So when it's when we do this in general, we don't think about these absolute values. But once it comes to having to plug in something, we have to be careful, and so we have to really write absolute values here. Okay, so perhaps I don't think, I'm not insisting on this, but I'm sure that other instructors might say, no, this is wrong what you write, you have to write it this way. You have to write the initial the absolute values from the beginning. I have a bit discussion with my colleagues about this, but at the moment, in this case, it would have been better. You would not have the problem of ln minus 1. So think about it. It's basically only happens with the ln, right? So keep that in mind. That we should, technically, we should put absolute values there. We don't, because it's easier not to write there. But when we plug in things, we have to be careful. And then if it's a negative number, we really have to take its absolute value. Okay. And now everything becomes very easy, because what is that? The ln of, so this becomes minus ln of 1 times minus 1 minus c, right? Because 4 minus 5 is 1, minus 1. So this is 0, so we see that 2 is equal to negative c, so c is equal to negative 2. And therefore the solution is, here, so the solution is minus x squared minus 5 ln, okay, I'll write it now because I did it there, minus 2 times x squared minus 5, and why do I have, okay, there's something, I think I made, what did I do wrong? Oh, it's not, it's 7. Y2 is 7, not 2. I'm so sorry. 4. I thought it was 4. I plugged in the wrong, I just did the wrong number. Okay, sorry about that. So I have to do this again. I plug in x is 2 and y is 7. So 7 equals minus ln, and we know already we have to put absolute values here, times 4 minus 5 plus c times 4 minus 5, okay? Okay, so this, of course, is 0, that we talked about it, so 7 is now minus c, so c is minus 7, and so our solution becomes y equals minus, let's write the x squared minus 5 first, ln x squared minus 5, absolute value or not, minus 7 times x squared minus 5. This might be not exactly how it is listed in the back of the book, and that's a bit what I'm saying. I don't insist that you simplify this, but it can be simplified, and for instance, this might be an occasion that you want to do it because you want to verify your answer with what was in the back of the book. So how do we do this? Well, we have a factor x squared minus 5 and in fact a minus sign, so if I factor that out, then I'm left with an ln x squared minus 5 plus 7. Plus now because I factor out the negative. And that's exactly how it was listed in the back of the book. Okay? So you see, there are quite of steps, and it's very easy to make a mistake in one of these steps, and there are a lot of pitfalls, and you see how I blundered a couple of times, but so that's why these things will take time, and so take your time for this, solving these things, go over it, check it with the back of the book. If it looks almost like that, you can say, okay, probably I made a small mistake, but if it's kind of getting really different, you might think, okay, I made a mistake, so let's go back over it. Of course, in a quiz, you don't have that luxury. So especially when you have to do this on a quiz, take your time. You have the whole day for a quiz, so don't rush it, okay? You double check your answer. Now, in principle, you can always check your answer by plugging this into the original equation, but that is not something simple to do. It requires, I mean, not simple, it's time consuming, because you have to take derivatives, and these are pretty ugly functions, if you ask me, okay? Okay, all right.